All right, let's pull back the curtain on a world that you rely on every single second, but probably never ever think about. We're talking about the hidden language of industrial engineering, where the tiniest details are the only thing preventing catastrophic failures. I mean, just imagine this for a second. An entire factory. We're talking hundreds of workers, millions of dollars in production, just grinds to a halt. And the cause? It's not some huge explosion or a massive breakdown. Nope. It's just one single wrong digit buried deep in a line of code. It honestly sounds like something out of a movie, but you know what? In the world of high-stakes engineering, this is a constant reality. So how in the world do engineers stop these disasters from happening? Well, they have to learn to speak a very, very specific language. And today, using a professional training manual as our guide, we're going to decode some of these invisible instructions that literally keep our world running. Okay, first up, we're going to decode a valve's brain. We're looking at a little device called a Samson positioner. Now, this is the small, intelligent part that controls immense power inside a massive industrial system. And yeah, it might not look like much, but if you get just one tiny detail wrong here, the entire system can fail. So what does this thing actually do? Well, picture a dam operator who needs to release a very precise amount of water. They can't just run down and turn some giant wheel, right? Instead, they send a tiny electrical signal. This positioner is what gets that signal and translates it into enormous pneumatic force. That's just force from compressed air to open or close a massive valve with absolute pinpoint accuracy. Now, here is where it gets a little wild. When an engineer orders one of these, they don't just ask for a valve positioner. No way. They use a model code that looks like this. I know, it seems like a total mess, but it's actually a language where every single digit has a critical meaning. Let's just focus on one digit for a second, the fourth one. If that digit is a 0, the device will open the valve, sure, but the operator back in the control room has absolutely no idea if it actually opened or by how much. They are completely flying blind. But if that digit is a 1, the device sends a signal back to the control room, confirming its exact position. Suddenly, the operator has eyes on the valve. Think about that. One single number is the difference between total control and complete chaos. So, a single digit can mean the difference between control and chaos. But what happens when the stakes get even higher? Let's move from the system's brain to its guardian angel. We're talking about the code for safety. This small box right here is a safety relay, and its one and only job is to watch for danger. It's connected to emergency stop buttons, to safety gates, to light curtains, those invisible barriers that protect workers. The split second a hand breaks that light beam or a gate swings open, this relay's job is to instantly and without fail cut all power to the dangerous machinery. There are no second chances here. Its role is totally non-negotiable. And just like our valve positioner, the part number is a code that holds all the crucial information. You can see right here, the part number 750104 for this PILS safety relay tells an engineer everything. The voltage it needs, how many safety contacts it has, and this is so important that it uses screw terminals for the wiring. If they accidentally ordered a model with spring-loaded terminals, well, the pre-made wiring on site would be totally useless. A tiny detail that could bring a multi-million-dollar installation to a dead stop. And this brings us to an even more critical point, which is highlighted by this quote directly from the training manual. It's not just about getting the part number right, it's about making absolutely sure the part is genuine. A counterfeit safety relay might look identical on the outside, but it doesn't have that guaranteed tested reliability. And when a component's job is to prevent injury or even death, getting the order exactly right isn't just about efficiency, it's about protecting human lives. All right, for our last example, we're going to move from complex electronics to something that seems, well, deceptively simple, a steel cable tray. But as you're about to see, even this humble piece of metal is governed by a strict code of engineering principles that prevent long-term, catastrophic failure. So here's a code that isn't a number, but a process. The absolute golden rule for these trays is that the protective zinc coating, that's the galvanizing, has to be applied after the tray is cut and bent. Why? Because if you do it before, every single cut edge is an exposed weak point, just waiting to rust, which could compromise the whole structure over time. The order of operations, it's everything. Now for the numbers. A cable tray can be loaded with hundreds, sometimes even thousands of pounds of cables. So how much can it bend or deflect before it's considered a structural risk? Well, there's a simple, non-negotiable engineering rule for that.
You take the distance between the supports and you divide it by 300. So, as you see here, if your supports are 1,500 millimeters apart, you divide that by 300.
And you get 5 millimeters. That is it. The maximum allowable sag for a 1.5-meter span of steel carrying all that weight is less than the thickness of 2 coins stacked together. That is the incredible level of precision we're talking about.
So, we've seen how one digit controls a valve, how a part number protects a worker, and how a simple calculation ensures a structure holds up. What's the common thread here? Well, it's all about how an engineer has to deal with information.
Let's end with a real-world scenario straight from the manual. Okay, you're the engineer now. A request comes in for a cable tray. The title says it's 100 millimeters wide, but the detailed description says 200 millimeters wide. Clearly, one of these is a typo, but which one? What's the right move? What do you do?
Really, you've got two options. You could guess, maybe the title is just a summary and the description is the right one. But if you're wrong, you've just ordered tons of the wrong steel, wasting a ton of time and money. The other path, the only correct path for a true engineer, is to just stop. You recognize the ambiguity, you pick up the phone, you send an email, and you get a definitive, confirmed answer before you do anything else. And that right there, that's the ultimate takeaway. It's not just about the machines themselves. It's about mastering the language that the machines speak. A language where a single digit means the difference between sight and blindness, where a part number is a promise of safety, and where a simple manufacturing process is basically a blueprint for longevity. In these high-stakes environments, ambiguity is the real enemy. Precision is everything.
So the next time you flip a light switch, or you turn on a tap, or even just drive over a bridge, just take a second. Think about the thousands of hidden codes, all the precise calculations, and all the unambiguous details that had to be absolutely perfect for that to happen. What invisible language, what devil in the details is keeping your world running safely, right at this very moment?